Thank you very much for inviting me and for all the attendees, who are participating to this presentation. It's a great pleasure and honor for me. So as mentioned, I will be talking about this emerging concept in wireless communications and networks, which is called, which is nicknamed Wireless 2.0. I will try to give you a little bit more details, and specialize a little bit what it means. But it's basically it's a kind of paradigm change in the way that we optimize and design wireless networks. So more precisely, I will be talking about this emerging concept that is called the smart radio environments or intelligent radio environments. And in order to make this vision true, there are two main things that I will be talking about. One is technology innovation, which is this RIS or reconfigurable intelligent surfaces or meta surfaces. And another one is the algorithmic part, which is basically the artificial intelligence. So I will be talking about these two things. So I give you a general reference about this the talk that I will be giving you today. So the main thing is that here you will find if you wanted the original idea that we proposed more than 1 year ago, with some examples that explain you what we mean by smart radio environments, and I will try to summarize a little bit with an example. So let's start with a simple example. So we are considering a communication network. So we have a simple case where there are a couple of base stations, and basically in these base stations, we see that there is also a mobile terminal. Usually the mobile terminal, what it does, it gets connected to the base stations from which it gets the best signal. In this simple case, this is going to be base station number 1, so this access point. This is in a very ideal setting, but in general, networks are much more complex than that. So we may, for example, have objects like in this case. So this object blocks a little bit the signal from this access point to the user, which makes this signal not that good, which implies that this mobile terminal is going to be served by this other base station. So still, the signal is not that bad. Still, it can get some services, but not as good as before, just because this base station was much closer to it. So the bottom line is that large objects, may reduce a lot the intensity of the signal intended to some users, and so the rate and the capability of having wireless access. So, but this is not necessarily the worst things that can happen. So there might be other objects, like in this case, where we have object number 3. And in this case, this object, you can think of a very large metallic reflector, for example, that takes the signal emitted from here and then it reflects it towards somewhere. Where, for example, there is a user that wants to detect the signal which was intended to mobile terminal 1. So these reflections, which we don't like and is unwanted, creates some security threats because this might be detected. But there is not much that we can do because this object operates and responds to the radio waves according to the nature, so the law of nature, the law of physics. Along the same lines, we may have another object. Think of a window. And for example, here we have a signal that goes from the outdoor to the indoor. And these users that are indoor are going to get some interference because of this signal. So what this simple example says? The simple example says that we have base stations that emits signals, and they need to reach some users. And but once the signal leaves the base station and interact with the environments, with the objects, so we cannot control the radio waves after they leave the base stations. We have some intelligence or capability of processing the signals at the base station and at the mobile terminals, but when they leave the wave, when they leave the transmitter, there is not much that we can do. And so we do not control these radio waves. So we can call this, which is how wireless networks work today, as dumb wireless. Dumb means no intelligence in the objects, but only at the endpoints, mobile terminal and base stations. So this simple example allows us to say 3 main things. The environment, so what there is in between the access point and the access point and the users, does not really play in our favor. So it makes our life pretty complex, and this is the reason why we need to develop always new technology in response to new services. Usually, ever since we have been playing with optimizing basically the access point, for example, by using very many antennas like massive MIMO or other things, or the receiver by using very sophisticated decoding techniques. But I mean, we have only adapted then to what there is in between the transmitter and the receiver. So what we have been doing is to try to identify when to transmit, if to transmit, etc., etc. But we have never been able to really modify the response of the objects. So we would like to change this status quo. We would like to change this way that wireless network works. And the final result is this. That's basically what we would like to have, that we call smart radio environments or smart wireless, as you will see in a while. This is the results. Then, I mean, throughout the presentation, I will tell you how we can get to this point, hopefully. But the idea is that we have the same scenario as before. Now you have this object 3 and object 2, where somehow we tell these objects, we treat these objects like they are an app, like they are an application. And we say, look, rather than doing what nature tells you to do, which means steer the signals toward here and steer the signals toward here, I program you in a way that you steer the signals where I want that you need to steer the signal. So basically, I modify this wall, I modify this window in a way that I get the response that I want. And if this is the case, I can get a much better signal here at the mobile terminal, which enhances a lot the performance. Of course, you understand that, okay, I told you this is called smart wireless if you want in short, but of course, we need to be able to program these objects, we will see how, in a very timely fashion, in an adaptive fashion, in a reconfigurable fashion. Because, for example, this eavesdropper, this user might be smart enough to identify that there is a reflection that basically has been modified here. It may intercept it. So in this case, we may need to program these objects by saying, look, reflect the signals to another direction, or just absorb the signals. Don't let the signal go through. The mobile terminals may move and other things may happen. So we need to do that in a very, I wouldn't say real time, but sufficiently fast. Okay? So this smart radio environment or wireless.2 concept is a sort of vision that says that we want to modify how wireless networks work today, so from adapting to the behavior of the environments into something that allows us to program the environments and to control the way that it modifies the radio waves. So let me be more specific. Today, so in a radio environment, which is not smart, what we do, as I told you, we optimize only the transmitter and the receiver. So we adapt the transmitter and the receiver, the access points and the users in order to take into account the environment. So what we do, we learn the environments, we learn where the users are, we learn the channel state information, and then we solve an optimization problem that allows us to tell us what to do here and what to do here at the transmitter and at the receiver. But we don't touch what there is in between. In a smart radio environment, we want to optimize transmitter and receiver jointly with the environment. So we still learn the environments, we still learn the configuration of the network, but then we solve an optimization problem where this environment becomes a variable to be optimized. So now we can optimize what the base station does, what the receiver does, and we can optimize also the response of the object. For example, to reflect the signals toward a given direction, to block the signals, and so on, and so forth. So we increase the opportunities, but also the challenges in optimizing the network. So in concrete, what does it mean? So programmability, we could say that in order to have this capability of telling the objects, programming the object as an app, we need a new technology enabler. And this new technology enabler is called, in this field, reconfigurable intelligent surface or reconfigurable intelligent meta surface. I will tell you what this is. And we need the algorithms that allows us to learn and to sense, to control the network itself. So indeed, we need the algorithms, which means we need machine learning and AI that allows us to make all this work. Okay, that's basically the idea. So I will be talking about these two things. First of all, I will give you a very short intro with a few slides to tell you exactly what they are, and then I give you some more details in the second and third part of this talk. So the technology, what is this reconfigurable terrain surfaces? I start with something in the next two slides. It's very long term, but actually a prototype exists. So this is basically a web page that you can find in the entity Docomo or website, where there is a news that in January 2020, Docomo basically realized a window, a smart window, a smart glass that allows us to modify the radio waves as we wish. It looks like this. It's a real window, which is transparent, so you can see through it. But when the lights, when the radio waves impinge upon the surface, they don't propagate through the window, and they are not reflected off the window like according to the law of physics, but somehow the glass is made of material that allows us to control how they are reflected. A simple way to visualize this is the following. Imagine that this is the window that you can see, the top view of the window that you can see. There is a transmitter that usually sends the signals. If this is a normal window, when the signal comes from this direction, you will get a reflection towards this direction, such that this angle and these angles are the same. If now you put here your smart glass, you may be able to modify this angle of reflection as you wish, according to some practical limitations. But you can see here that this signal, which was not useful for this receiver, is now actually useful for this receiver. And you have optimized your glass by taking into account the location of this receiver in an adaptive way. So this is what a reconfigurable intelligent surface, in a very simple term, is capable of doing through this technology. Okay, an application, I just copied an example from a website here from a company that is working on this. You have here an access point. You have a large building with a lot of windows made of glass. And imagine that you can replace all the regular windows with this smart glass. And then you may be able to steer the signal that comes here, that impinges here, towards directions where there are users which were not reachable by the access point itself because they were out of coverage. So you can enhance a lot the coverage without really affect the aesthetic of the building because you are just replacing the glasses. Okay. So now this is in short, what this technology is, and then we will see the details. How about the brain and the algorithms, the intelligence to make it work? Because you need to understand what the network scenario is in order to adapt to it, okay? So consider again the example that I showed you, maybe a little bit more detailed with 3D, where we still have the two base stations, one mobile terminal. Because of these large objects, you cannot really, get a good signal from here. You need to go through here to base station 2, which is farther. And so the signal is good, but you see, it's not that good. Now that we have this technology enabler of RIS, we could coat all the windows or the walls of our large buildings, or not necessarily large buildings, with these smart devices that allows us to modify the radio waves according to the status of the network. What we could do is to build an engine. We could build a controller that learns basically the configuration, the status of the network, and then is able to process this information, send it back to the smart surfaces, which are viewed as an app that is controllable via software. Okay, so you send back these control signals, and you program, you inform these surfaces what they need to do. And in this case, you may steer all the signals towards your mobile terminal and get a much better signal quality, and so to download the content much faster, or just being able to communicate. Okay, so that's what it is. Now, I want to give you some more information on these two aspects, so the technology aspects and the algorithmic part. Okay, so let's start with the first one. So let's see a little bit more concretely what an RIS is. So an RIS we can broadly define in my field as a new antenna technology. So it's a new antenna technology. It was it's very recent, actually, I need to say. You can find that it was recently also mentioned in this white paper here. Just some months ago. And you can see the kind of figure that you find. So there is a complex network where there is a surface, and you are able to modify the way that the signal are reflected off this surface or transmitted, I mean, through the surface. That's basically the main thing. But it's concretely is a new antenna technology with some specific characteristics. What you can do with this smart surface, in theory, you can do whatever you want. So we have already seen that you can reflect the signals towards directions that you like. You can transmit the signals. You can absorb the signals. You can focus, and you can do very other, I mean, fancy transformations. It just depends on the complexity and on what you really need. Okay, but in principle, you can do many things, not only reflections. How do they look like? I showed you already this example here, okay, which is maybe the most long-term that I was able to find to date. But there are different types of RRIS. So some of them are based on metamaterials, like this one, like this one, like this one. They can have different sizes. So here you can see 1 square meter. Here you can see 6 square meter of surface made of very tiny antennas. And here there are approximately 4,000 reconfigurable tiny antennas that work together in order to being able to shape the radio waves. And here you can find another example that maybe is the easier to explain. You have the surface is made by these 4 tiles, and each of these tiles has some reflecting units that are in yellow. Each reflecting unit allows you to modify the phase of the signal that comes in. And by optimizing the behavior, the response of each of these yellow patches, you are able to transform the radio waves as you want. So technologically speaking, you can implement it in a different way, but the vision is to modify the radio waves, okay? More in detail, if you want to have more details, basically, you can always draw a picture of this kind for an RIS, which is you have tiny antenna elements, or that are also called reflecting scatterers in red. They are not necessarily the same. They can be the same or they cannot be the same. As you can see here, they can have different size, different shape. The important things to know is that you need to have also some tunable elements, which can be some varactors and diodes that are distributed throughout them. And depending on how you set these tunable elements, you change for example, the direction of reflection from 5 degree, 10 degree, 20 degree, and so on and so forth. Okay. As we will see in a while, the nice characteristics of this surface is that we want it to be as passive as possible, but it cannot be completely passive because you always need to have radio interface in order to receive the configuration signal and to tell these tunable elements what they need to do, how they need to be configured, for example. Okay. So what do we do with this RIS? In principle, people are trying to use them for any kind of possible applications that you can imagine. Of course, I mean there are scenarios that it's more realistic, less realistic. Other scenarios where you can get a bigger gain. But I mean, more or less, all the times that you are close to a surface, you may interact with the surface in a way that you can enhance basically your communication capabilities. Okay, so the applications are very many. And so far in wireless communications, people have been using them for multiple objectives, for enhancing the coverage, for increasing the throughput and rate, for enhancing the security, for reducing the amount of interference in the context of UAV networks, Li-Fi networks, millimeter wave communications, indoor, outdoor. So Industry 4.0, there are many applications. So it's really a matter of deciding what you are interested in. Why they are so different? They are so different because, as I mentioned, they are meant to be as passive as possible. So we don't really want to have power amplifiers like we have in typical network elements that we have today, like access points, base stations, or relays. Okay, so nearly passive means that always we need to learn the channel, we need to learn the environment, and then once we learn, we can configure the system, and then we can operate the system for some time. Basically, nearly passive means during the normal operation phase, they can be passive. So the definition of nearly passive for us is that you have no power amplifier, you have minimal digital signal processing capabilities, and you have only minimal power for controlling the reconfigurable elements, the tunable elements. This would be the dream. Okay, that would be the objective. In practice, I mean, how much can we gain in terms of power reduction? This is just an example that I found in the website of this company, Pivotal, that is developing this kind of technology for antennas. That's just an example that I found in this website, so I will just show you quickly. So this is the, if you want, a conventional system with a phased array with many elements that consumes around 40 watts in total. Then we will see the details. And this is an RIS, or which is also called holographic beamforming for this company, in this website. It consumes only this, so more or less 3 times less than a phased array, while providing, in theory, the same performance. So you can see the reduction in terms of power that we have. Of course, there is a price to pay. As you can see here, there are 256 elements of this phased array. Here we have a little bit more. We have 600. And we consume also a little bit more for the programmability. But even though we have this, we still gain 3 times in terms of power consumption. So what we have understood so far is that this RIS usually have a very large number of scattering elements, more than what we are used to see. These yellow patches that I showed you in the previous figure, but they are much less expensive than each element that you can use for conventional devices, and we don't have a power amplifier. So it's true that there is no free lunch, but at the end of the day, if we do the things well, I mean, we can increase the number of elements by keeping the size reasonable, but I mean, still spend much less. So now people are talking about this concept. So they view RIS as a software-defined architecture, which is realized a reduced cost, size, weight, and power. And this is called now CSWAP design, which is different from what we have been doing. So what are the main capabilities? First of all, one of the main concepts that we need to understand here is that through these devices, since we don't have power amplifiers, we do not create new signals. We do not pollute the environment with new RF signals, but we recycle the signals that exist in a better way. So we can reduce the amount of electromagnetic radiations that exist, so to have a low EMF exposure. We just recycle the waves. And also, if we look at this long-term solution, they don't look that ugly. They look quite nicely. They are really aesthetically nice. And they may also be made of recyclable material. So there are a number of pros advantages that push us basically to look into this technology. So what I can say then is that with respect to what we have now, what we aim for in wireless 2.0 is that to have networks that are not dominated by active devices, that we have power amplifiers like base stations, relays, and similar things. But we really want to have a network where we have active devices, but also, passive components that work together in order to increase the capacity, the rate, get a better performance, but with low and affordable cost and power consumption. So, and the idea is to achieve that through a hybrid network where there is a combination of passive and active devices. So RIS is not, at least of today, a technology that will replace what we have today, but rather something that will complement what we have today in order to find a good trade-off depending on the application and the scenario, in order to still get good performance, maybe improve the performance, but definitely by reducing the cost and the power consumption and the complexity. So that's a little bit the one side of the story, which is basically the technology. So we need this technology in order to make the network reconfigurable in a way that the environment is reconfigurable and can be part of the optimization space, while so far only transmitter and receiver have been part of the optimization space. So now that we understood that, we can look at the, assuming that this functionality is available, how can we make it work? And what is the role played by machine learning and data-driven methods in this context, besides the techniques that we use, have been using for so long time in wireless communications? And that's how we'll try to answer these questions in this part. So first of all, here I really would like to emphasize this term, which may seem a little bit, I mean, not clear or maybe strange, because usually this artificial intelligence, machine learning, they are always, coupled with data-driven methods. So we need a lot of data, and we want to process data in order to optimize the network behavior. But here we call it on purpose model-aided artificial intelligence, to say that that in wireless communications for optimizing the network, we have always been using models, so mathematical models. And now they seems to be not sufficient enough, because the system is getting so complex that the models are becoming so inaccurate. And so that's the reason why machine learning has become so popular in large scale network optimization. So we would like to see the interplay of these two things. So do we really need to abandon models and just use data, or maybe there is something else? So in fact, the question is the following. From the wireless perspective, a wireless researcher could ask, what can machine learning do for me? So what machine learning bring to my field, communication theory, wireless communications, that I was not able to do before. But from the point of view of a machine learning researcher, maybe the question is, okay, I do have the algorithms. What your communication theory, what the theory that you developed for so many years in wireless communications can give me in order to maybe improve the algorithms or to understand the algorithms a little bit better. So that's the things that I would like to discuss. And so the idea is to try to maybe develop tools that merge together models and data in a way that we can get better, can somehow take advantage of the advantages of both of them, but we can somehow overcome the limitations that they have. And so I will discuss this. So let's take an example, as an example, a general networks, the one that, for example, I showed you in the previous part of this presentation. Then I will go back to the end to this point, but where there are access points, there are RISs, there are all distributed. And usually, how it works? It works that we have some inputs. For example, this can be the location of the users, this can be the location of the buildings, this can be the location of the RIS. And for example, we want to get some output variables, which is, for example, how much power the user should use, what kind of functions the RIS should implement, for what? For optimizing something, which can be the data rate, which can be the coverage, which can be anything that we like. And usually, we formulate this in terms of an optimization problem, and we will see what it means. But this can also be viewed from a data-driven method or a machine learning view as a mapping. Basically, if I'm able, for any input, for any locations of the users, for any locations of the RIS, or for anything else, give you what the optimal configuration of the network is, and I'm able to figure out what this function is, this is just a mapping. I don't need to solve an optimization problem anymore, just a mapping. So if the users are in position X, I need to use this power. If they are in position Y, I need to use another power. And this is then a typical classification problem in which we could solve by using machine learning. So this is a little bit the reason why it's pretty popular now in this technique in optimizing wireless networks. So let's go a little bit more into the details. So let's take the data-driven approach as the approach that we need to use, and let's study what the pros and cons are. So what do we do if we have a lot of data? If we have a lot of data, we get all this amount of data, and then we feed it into, for example, a deep neural network, and we optimize this deep neural network to act as a classifier, for example, in order to get the optimal resource allocation. So the amount of powers to transmit, the function of the RIS to use. So what are the issues with this approach? We need a lot of data, usually, to make it work. And we also need to be able to interpret all this data, which is not always that trivial. And also, with brute force optimization, that we all know that we need to spend a lot of time for training these neural networks. Even though there are techniques, when you change the problem, you need to rethink whether the techniques that are known can be applicable or not. So it takes quite a bit of time to identify the good architecture that works in all the cases that you need. For the interpretation of data, I guess that you are quite all familiar with this example. So even though you get a lot of data, you may give the wrong interpretation to the data set that you have. And if you give the wrong interpretation, basically you may just design the system in the opposite ways as basically should be done. So I guess that you are all familiar with that, but you can find the details in internet as well. So let's now have a look at the conventional communication theoretic approach. So what we have been doing in wireless communications before machine learning became so popular, at least in our area. So what we usually do, we write down an analytical model for the network, which is sufficiently accurate, but of course we need to avoid many details. We write down an optimization problem, maximize something subject to some constraints, and then we get the outcome. What is the issues? What are the issues with this approach? First of all, usually, even though the wireless model it's pretty relatively simple, you end up having non-convex mixed integer optimization problems. They are very difficult to solve, especially they are very difficult to solve in a real-time implementation because you need to be able to solve them before or any time that the channel condition changes, every time that the network evolves. This implies that it's not so easy to do that. An option to overcome this limitation can be, okay, let's forget to use conventional optimization theory. We can use machine learning. What does it mean? We create our data set from a model, so it's a synthetic data set, and then we can optimize machine learning as we are used to do, these neural networks as we are used to do. So now here, after the training stage, everything gets very simple because here we just need to do some multiplications. So it's much easier than what we were doing before with conventional techniques. But what is the problem? As I said, we rely on a model, and this model may not be accurate at all. They may not correspond really to reality, or may not be that close to reality. So the point is that, for example, I can give you an example. This is taken from some papers of mine, which have been doing a lot of mathematical modeling in the last few years for modeling large-scale networks. But if you take any parts of my paper, this is one of those. You say, let's make an assumption which is made because otherwise we are not even able to write any functions. So now, whether these assumptions works all the time or whether it is 100% realistic, it needs to be discussed. And besides making assumptions, most of the time we rely on mathematical simplifications just because otherwise we cannot reach any point. So this, of course, is something that machine learning, an issue that machine learning does not have. Okay. So now the question is, if we consider a system where we have a large-scale network, where we have a randomly spatially distributed RIS, which have a very complex behavior that can only be modeled by using Maxwell equations, you can understand that we really need to make a bunch of oversimplifying assumptions in order to be able to get any useful analytical model. So it might be pretty complex or not straightforward to develop a model and to obtain and to write down an optimization problem that can be solved that is realistic, sufficiently realistic. Okay. So once we understand these pros and cons, the idea is that, okay, let's start from an approximated model. That is the only best that we can do. We acknowledge that this is the best that we can do. And maybe we can also make the assumptions such that we could easily train this neural network. But then why not using some data in order to refine the mismatch of the model? So the idea is, rather than choosing between modeling and data, let's try to use them, combine them together in a way that we can see whether we can get maybe better performance. So here I emphasize that we want to reduce. Here we want to make the model. That's the point. Accurate enough, but not mathematically intractable, because otherwise it makes no sense. And here we would like to use an amount of data that is not huge, but is sufficient to correct the mismatch. So these two things are tightly coupled. Okay, that's basically the main idea. So in general, I mean, you can have many cases. In wireless, what you encounter most often is this one. So what I described to you is essentially what always happens. We are able to write down a model, but we need to make a bunch of assumptions. So that's example that I showed you of combining modeling and data makes, at least according to what we understood, relatively sense in designing wireless networks. Okay. So let me show you now an example to see whether it works or not with a simple example that we studied recently. So the idea is that we get a physical system, as I said, we get an approximated mathematical model, we optimize an artificial neural network based on the data set of the model, and we get an approximated representation of reality, which is not exact, but it's just approximate, but sufficiently good to the model. Then what we do, we take some measured data and we refine, we create another artificial neural network that takes as an input the features extracted from the model, the live data, and try to get the actual representation of the system. Okay. So the question is, how can we combine these two things together? The idea is, as I said, input model based on model. You create a model-based neural network. You get these features. You input them with your data in another artificial neural network that you optimize, and then you get the system. More concretely, what we did in the example that I will show you, just as an example, we took a model and we identified the architecture of the neural network by randomly choosing the bias and weights during training, starting from this random initialization. And the scope of this first step is to really identify the number of layers and the hyperparameters, number of neurons, okay? Number of layers and number of neurons, in order to identify the architecture. Once this architecture is done, what we did, okay, assume that the model is good enough in order to reproduce these features. So we assume that the number of layers and the number of neurons does not have to be changed because the model is sufficiently good. We just use the data, in blue here, the input data, the actual data, the live data, just to optimize the bias and the weights. And the idea is, does it work and what is the gain? Okay. So let me give you an example. We started from a model, and this model, we consider a very naive model, which is very used in wireless communications because it's simple mathematically, which is modeling the base stations as randomly distributed, completely randomly distributed. This is called the Poisson point process model. And then we assume, okay, assume that on the other end, the actual data that we have looks like this. So they are more regularly deployed because the city where we are considering allows us to put the base stations in a more regular way. So what happens here? So of course, I mean, this cannot be a good representation of this one in general if I just look at these two snapshots here. Okay? So what we did is the following. We first created a neural network based on the model. So we learn that point process, and then we refined that, and then basically we refined the initial model by learning the new model starting from the initial one. And we used as a tool that is called deep transfer learning, which is basically a technique that I described to you before that allows us to transfer the information from one neural network to another. Now, let me give you an example. So imagine that, this is the transmit power of your access points. And this is the optimal number of access points per square meter that you need to have in a given area based on the transmit power that you use. So there is an interplay between the transmit power and the optimal density, the number of access points per square meter. And assume that somebody gave to you the actual solution, the optimal solution. So it's a genie that gives to you the optimal one. Now, assume that you start your analysis by using this model, the Poisson model. If you solve the problem, you get this answer. This is your prediction. The prediction tells you that if you have 10 dBm of power, your optimal number of base stations per square meter is going to be this number here. But the reality tells you that this is this one. So the system, you are going to optimize the system in a very suboptimal point. Let's now take data, only data, but not so much data. Assume that you have 3,000 samples. And if you use 3,000 samples to train your neural network, you will get the green line. Now, the green line can be considered to be a little bit better than the black line but still is not that accurate as the blue line. Of course, if you increase the number of data, the amount of data, you are going to be much closer to the blue line. But here the question was, I have one approach, black, which is not working. I have one approach, green, that is not working. Can I combine them together and see whether I can get something better? If you do that, so if you start from the model and then you use these 3,000 samples for refining it, you get the red line. And the red line is much closer to the blue line. So basically you are taking a model which has a disadvantage not being accurate. You taking the data-driven approach, which in this case has the disadvantage that we don't have a large amount of data, but you can merge them together in a smart way and you can get what basically you want. So this is an example that combining data and modeling seems to be feasible or a good idea in this scenario. Okay. So I conclude the last couple of minutes by just saying that in my field, at least, I mean, wireless communications and networks, there is increasing interest in this concept of smart radio environments, which basically means programming the environment. So treating the environment not as something given, but considering the environment as an optimization variable that you can play with, that you can tweak with the transmitter and with the receiver, which is something that we have not done in the past, at least I mean in this in the way that we are talking about now. And this is basically what is called wireless 2.0 because it changes a little bit the way of thinking the environment itself. And we have understood that there are two components in order to make this possible, or possibly possible. One is the technology enabler, which seems to be given by these reconfigurable intelligent surfaces or meta surfaces, depending on the actual technology that you use. And then you need some distributed intelligence, maybe reinforcement learning techniques and transfer learning, deep unfolding, deep neural networks. I mean, all these powerful algorithms that allows you to overcome the modeling limitations and at the same time allows you to really optimize the system by taking into account the real data. And now from machine learning, I think you all know where we are. So there are powerful techniques. We just need to be able to use in the good way. But where we are in terms of reconfigurable intelligent meta surfaces. So the nice part is that this is a very hot research field in the sense that people started working on reconfigurable meta surfaces, truly reconfigurable meta surfaces, quite recently. And so even though in wireless we assume most of the time for understanding the potential gains that some functions are available, actually these functions are being developed by our colleagues who are working in electromagnetics and in the materials. So this reconfigurable meta surfaces seems really to be the next generation of meta surfaces, at least I mean according to experts. So if you want, I mean in wireless, we are already talking about the 6G, whatever it is. And in meta surfaces, we are waiting for the third generation of surfaces that are actually reconfigurable and that allows us to do what you can see here in figure number 1. So turning a radio environment to a smart radio environment. So you can think of this wireless 2.0 as the combination, I mean, of these two things, plus, of course, machine learning. So the intriguing part for me in this field of research is that we are, most of the time, we have looked at the communications and electromagnetisms of material as two or three independent, I mean, things. But now, I mean, in order to really, exploit this RIS, these smart surfaces in wireless, we really need to reunite a little bit the theories of communication, signal processing, information theory, and electromagnetisms, and physics and materials, in order to be able to really understand what the limits and the opportunities are, because we cannot oversimplify too much the how these surfaces actually operate, and this is what I'm trying to work on these days. Regarding the artificial intelligence, is not really, there is a lot of research now in wireless communications about that. It's not really whether modeling or data, modeling is better than data or data is better than modeling, but maybe it's how we can use both of them in order to make something good out of them. And of course, I mean, it's not only reuniting all these things, but also reuniting with machine learning, especially if we want to exploit modeling and machine learning. I think that we need to understand the limitations of the models and the advantages and limitations of machine learning in order to try to make the good choices in terms of combinations of them. Just for you to know, if you are interested, I'm relatively active in the IEEE Communication Society. Recently, I mean, just really, I mean, in the last 2 months, actually, we established a few initiatives on this emerging field of research, RIS. So we created some special interest groups that are focused on developing this technology from the wireless communication point of view, from the signal processing point of view. And also we created an emerging technology initiative that bridges together people with expertise on communications, wireless networks, electromagnetics, metasurfaces, machine learning, and etc. And if you are interested, we also have a best reading sections in the website of the IEEE ComSoc. You can just find it in internet, where there are many recent papers that have been published in this field of research. So if you want to know more, of course, you can get all these papers, all this information from my webpage here. As you can see, the most recent papers are related to RIS and also the combination of RIS and machine learning, but you can find the details in my webpage. So from my side, I would like to thank you for inviting me to this talk. I just would like to close by saying that the research activities conducted in this presentation are supported by the European Commission, in particular a European project called Ariadne, with a focus on reconfigurable intelligent surfaces and artificial intelligence to develop new wireless networks, especially wireless networks that operate at very high frequency bands, and in particular in the D band. So this is my email. So if you are interested in further details, material, or you just have questions, just feel free to drop me an email, and I will be really happy to interact and to discuss with you. So once again, thank you very much for joining these presentations on Wireless 2.0, and thanks.
Thank you so much for the wonderful talk. It's really nice to see the progress in terms of the material, how material science, signal processing, wireless communications all integrate to each other. And now we are going into AI field, which is quite interesting. Okay, now let's move to the Q&A session. So I'd like to invite my colleague Vishnu to take over and go through the questions that have been asked by our colleagues here listening to the talk. So Vishnu, good afternoon or good evening.
Thanks, Thomas. Yes, good afternoon. I just, there are many questions. The chat window has been quite active. I just want to make sure that we are on time, and also I'm going to maybe take some elements of these questions and add some my own interesting aspect. So it's a very interesting talk. Thank you so much for the talk. There are some questions which touches this aspect of positioning and I think the calibration of where and how these surfaces has to be placed. And you know, from our experience, we already know that operators already have a lot of headache configuring the existing antennas themselves. So now if we add these surfaces and how sensitive they are to the accuracy of positioning and the what should I say, the angle which is required for the best experience that you explained. So could you explain a little bit about this aspect? How sensitive are these? You know, the windows that you explained, if let's say the angle changes, my entire configuration goes for a complete disorder. Is that the case, or could you please explain what happens?
Yes. So this is a very good question. So thank you very much, and it's really a key question, so that a key issues. I mean, that many of us are trying to understand, explore, because it's really important in order to get the gain that we expect basically to get. So so I think that there are two points in these questions. One point is the impact of the location of the RIS, so the positioning of the RIS, and then the impact of the how accurate we should be in optimizing the response of the RIS once we have identified the good location. So going to the first point, the location. So it's really important, I mean, to identify the good locations. So usually, I mean, what we would like to do is to put the RIS in a way that, in a position that they can clearly see the base station. They can clearly see the access point without no obstruction, without no buildings or walls in between them, such that we can really get a very strong signal that can be reflected off. So that's one vision. Studies, also I mean experimental studies, but also analytical studies have shown that the RIS provide the best performance when they are either very sufficiently close to the access point or when they are sufficiently close to the receiver. So these are the two opposite locations. They seems to perform quite, I mean, they don't perform extremely well in the sense that they don't give the best performance when they are, for example, in the middle between transmitter and receiver. This is interesting to know because it's also to mention because is really different from other hardware devices that we were used in the past. So so one idea is that to put them close to the base stations with a strong line of sight. Another is to use the RIS for cell edge coverage enhancement. So to put the RIS at the cell edge such that they are close to the mobile terminals. And when the mobile terminals are close to them, you communicate to them. And this seems to be another good deployment. So this is what we understood so far. Of course, there are many of us trying to identify what the best positions of the RIS should be, assuming that we are able to choose the positions, because this might not always be the case. Another vision is, and there are some studies that assume that we cannot control the locations of the RIS because we cannot control the site, or we cannot control the best site simply because they are too expensive or it's not convenient to put the devices there. There are some studies that have shown, even though you put this RIS quite randomly in the sense that you don't really control the optimal locations, but you are able to tune their response, then you don't get the best performance, but you still get a sufficiently high gain as compared to what we are doing now. So there is no clear answer at the moment, but this is basically what we understood so far. Okay. Regarding the capability of tuning the RS, this is a very good point. And actually the answer is less clear than the previous questions, because in wireless communications we are used at the beginning always to formulate the problem in a very optimal sense. So let's assume to know everything, and let's see how much we can get. Simply because if we get poor gains by doing that, then it simply doesn't make any sense to go ahead. So that's so far most of research has been focused on doing that. So the huge gains that we have noticed are because we know everything. There are actually, I conducted some research recently with some colleagues trying to estimate, to assess the impact of learning this amount of information in order to be able to optimize the RIS. And the result says that if we don't develop the learning algorithms, the channel estimation algorithms in an efficient way, the overhead for acquiring the optimal configuration may offset the gain that we get from using the RIS. So it's really a matter of developing the good algorithms for channel estimation that reduce the overhead as much as we can, etc. Other studies have shown that, of course, I mean, you cannot control the RIS very fine exactly. So you may not be able to steer your beam 0.1 degrees resolution, or so you need to be able to do it in a coarse way. And so, I mean, there are studies showing that. The studies have shown, these are surprising in the positive sense. They have shown that even though you quantize, it depends how much you quantize, but even though you quantize, they are still pretty good. The performance is pretty good, even though you lose something. Recent results show that there are some prototypes with very brute force quantization, like optimizing the phases with an error of 180 degrees, so zero pi. Recent results show that in this case you lose quite a lot. But as long as you are able to at least to have a 90-degree, 45-degree resolution in terms of tuning the optimal phases, you can still get the asymptotic, the same asymptotic trends, but you have an absolute loss. Other things that, but I mean, there are now studies. This, I mean, I cannot say much because we are working on that right now. But we are actually working on studies in order to do some long-term optimization for the RIS, which do not really exploit the instantaneous channel state information, but it's more long-term optimization. And we have seen that you can get quite good gains in an indoor environment, much less in an outdoor environment. But in an indoor environment, since the distance is much shorter, you can get good gains. So this is not published yet. It should be out, I mean, in a few weeks. But we are actually investigating that. And so basically, the answer is, as usual in wireless, there is actually a trade-off. But the results seems to be not as negative as many of us were thinking at the beginning, because the feeling was that the overhead was really huge, and also the sensibility to the channel state information was very, very high. But it seems to be, we do have this phenomenon, but if we develop the things smartly, we should be able to make it work.
Thank you so much. It's very interesting. In fact, you covered very interesting points which are upcoming as well. In fact, you covered some of my next questions with respect to channel estimation. You touched upon that. There are some questions around how real time this has to be. I mean, in one of your figures, you did show the outdoor and the indoor, and there was a person walking. so mobility seems to be there, but that's the question. So how real time this has to be, and do they handle mobility, and are they dynamic enough?
Yes. So yeah, that's a not very interesting point. We don't really know the final answer. So so far we are studying that. What we basically understood is that of course, I mean, it's this technology. It's more suitable, or at least, I mean, in the short term for sure, it seems to be more suitable for indoor applications, which of course are not as dynamic, where the mobility is not that high as in the outdoor. It seems to be a little bit more challenging in outdoor because of the mobility. So I can tell you that there are some test beds that have been implemented in the Wi-Fi band by researchers in the US. I've shown actually the figures of these test beds. One is called RF Focus, another one is called Scatter MIMO. And they have made some actually experiments in indoor, and they have shown that they can actually handle the typical mobility scenarios that you have in indoor. So there are actually numbers where they show how fast their switches can be turned on and off, and also, I mean, the number of packets, so the latency that you need in order to acquire the channel state information. So for this kind of applications, it seems to be indoor, low mobility. It seems to be much more practical now. Outdoor scenario, I'm aware of only one trial that was made by Docomo at the 2019 in Japan. He was surface mounted on on a vehicle, and this vehicle was moving, and they were able basically to track the vehicle and to enhance the data rate. Now, I don't remember actually the speed, the velocity that they used. I don't even remember if it was cited, but there are actually people working into that as well. Of course, now, I mean, many people are mostly looking at the indoor for the moment.
Very interesting. I think it's very exciting, the future work which you mentioned as well. It is, there seems to be a lot of possibilities, and personally I think that some of these are very amenable to the AI ML type approaches. It's quite an interesting field. I think we covered most of the questions. There was one about what is this material. There is a lot of curiosity as to what type of material would make the surface that you mentioned. I know there is a project which I think a European project which works on this type of developing this material. Could you and I think you mentioned in your paper also the distance between the units has to be a function of the lambda. Could you explain what kind of material is, what are the characteristics of the material which is used for this purpose?
Yeah, that's very good point. Yes. So there are actually, at least, I mean, I think that the material, I mean, okay. If you ask these questions to a person who is working in metamaterials, I mean, who builds this kind of device. So I'm not building this kind of devices. I'm working with people who build them, but I'm just using the models basically that they provide to me. I think that if you ask these questions to a person who built these materials, he can tell you that there are really many possibilities. Even, I mean, there are new materials. If you just think at the window that I showed you from Docomo, I think that there are really very new materials that allow you to do what basically you want to do. And also, I mean, what I know is that it depends on the frequency, operation frequency. So there are actually surfaces that can operate in the Wi-Fi band, millimeter wave, deep band, terahertz on light. I mean, so it's really, I mean, depends on the operation, on the function, and on the frequency at which you operate. In wireless communications, I mean, we have two different approaches that allows us to implement these surfaces. One is the conventional one that is useful. I mean, is more understandable for people in our domain, in my domain, and with background on antennas, which is basically really considering discrete antennas. So the antennas are usually small antennas, like lambda over 2 of size, more or less, and they are also spaced by lambda over 2. Here, the models are more or less more conventional than actual metamaterials. Metamaterials is really when the antennas are much smaller than lambda, so lambda over 8, lambda over 10, and also the distances are much smaller than lambda, so lambda over 4, lambda over 8, etc. So what is the prototypes that are working now in wireless, fully functional prototypes in the US, they are based on discrete elements, simply because they are built in a university lab. So that's basically, it's much easier to rely. The difference between these two is the actual performance that you can achieve. So if you have unit cells that are spaced much less than lambda over 2, you have a much better capability of controlling the radio waves, especially when you are close to the surface, so in the near field. But especially you are able to create some surfaces that are very efficient. Usually these surfaces, they lose efficiency when the angles that comes in, it's very different from the angle from towards which you want to send the signal. So when the difference between incident and reflection is very large, the efficiency is not very high. With metamaterials, well-designed metamaterials, sophisticated metamaterials, you can actually get very good efficiencies even in those cases. And this is the field of research where experts in metamaterials are putting their attention basically now. So you can use a variety, I mean, of materials. There are also acoustic surfaces. So for us, I mean, wireless communications, I guess that most of us for the moment are thinking to these discrete antenna elements that, even though they are not the best one from the technology point of view, still allows us to get quite significant gains. Yeah.
Very interesting. I think I completely. I remember your paper where you talked about this perfect anomalous reflection. If I remember right. Yes, yes. I think this is a quite interesting concept. And also just a few comments. The way you mentioned about training and the overheads in training, as well as the transfer learning, deep transfer learning. These are concepts which we worked on last year in ITU. This is quite relatable, and it's quite interesting. I can't wait to see the future of your research. As well as what this surface will do to channel estimation itself. I mean, I can't even imagine the kind of changes it will bring into path loss and the channel estimation. Unfortunately, we are actually over time. Fortunately, our audiences are still here. That means that shows the value of the explanation that you have done. Thank you so much. I think the question answers which you have given has been much more valuable. Also, in addition to the explanations that you gave with the slides. Thank you so much for staying over and explaining these questions. Over to you, Thomas.
Thank you so much, Vishnu, for moderating the Q&A session. We really appreciate for taking most of the questions and having this exciting talk. We thank you so much, Professor Marco Direnzo, for the wonderful talk. It's been quite interesting to see what the future is coming with the wireless 2.0, where we are going to be able to control the environment, not only the transmitter or the receiver, but as well as controlling the environment. It's quite interesting. I would like also to thank all the participants who attended today's session. Thank you so much for participating.